Welcome to the Deep Dive, the show where we sift through the sources to extract the sharpest insights tailored just for you. Today, we're taking a foundational plunge right into the world of statistics, the absolute building blocks for anyone, navigating data science. Our mission, well, it's to take your raw material, primarily those bedrock concepts from practical statistics for data scientists, and transform them into clear, actionable knowledge. We're here to give you that shortcut, that distilled understanding of the statistical backbone, the stuff underpinning modern data analysis. The goal is really to illuminate not just what these concepts are, but crucially, why they're important and useful from a data science perspective.
Yeah, and what's truly fascinating here is how timeless these principles are. I mean, even with all the buzz around big data and AI, the ideas John Tukey championed decades ago uh, in exploratory data analysis, they're more relevant than ever. This deep dive will hopefully illuminate those essential statistical ideas that really help us make sense of the vast, complex torrent of information we're all swimming in. Without these fundamentals, you're essentially trying to navigate an ocean without a compass. It's that basic.
And that's exactly where we start. Our source emphasizes exploratory data analysis, EDA, as the first and most important step in any project based on data. It's like getting to know your ingredients before you even think about cooking, right? So for a data scientist, what's the most crucial, maybe, mindset shift ED demands?
That's a great question. The mindset shift is moving away from immediately trying to model or predict to simply listening to your data first. Tiki's genius was in making us really look at the data first. It's about discovering patterns, spotting anomalies, forming initial hypotheses, rather than jumping straight to the complex algorithms. It's the art of curiosity before, the science of computation.
I love that, the art of curiosity. Okay, now before we can even get curious, our data often needs a bit of shaping, doesn't it? Things like images, text, or those endless streams from IoT devices, they're typically unstructured. How do we take that raw chaos and make it, well, statistically digestible?
Exactly. For statistical concepts to apply, we almost always need to process that raw, unstructured data into structured data. Think of it as organizing everything into a neat table, rows and columns, just like a spreadsheet. And the why this matters is profound. The type of data, whether it's, say, categorical, ordinal, or numeric, is paramount, absolutely critical. It dictates everything: the right visualization, the appropriate analysis, even the statistical model you should eventually use. Your software, whether it's R or Python, interprets these types differently, and that impacts everything from performance to, well, the validity of your results.
So if we're talking tables, the typical frame of reference for most analysis in data science is what our source calls rectangular data. For someone just getting their bearings, how would you define that? And what are the essential terms we need to know within that structure?
Rectangular data is, well, exactly what it sounds like. Data organized in straightforward rows and columns, like your everyday spreadsheet or a database table. It's the real workhorse of predictive modeling. In data science, especially with tools like R and Python, we often call this a data frame. Each column in that data frame is a feature. You might also hear it called an attribute, input, predictor, or variable. Lots of names for the same thing, really. And then there's the outcome. That's the specific target variable you're often trying to predict, maybe a binary outcome like whether an online auction will be competitive or not. The key insight here is that the data frame isn't just a container. It's this really versatile structure that unlocks powerful manipulation and analysis. It's the bedrock for almost any modeling task, you see.
That makes perfect sense, yeah, the fundamental building block. But what about data that doesn't fit neatly into those rows and columns? Does that happen often?
Well, absolutely. It's true that rectangular data is our main focus for much of this foundational work, and it's definitely the fundamental building block of predictive modeling, like the source says. But it's important to acknowledge other specialized structures exist. We have time series data, crucial for forecasting, where measurements are taken over successive periods. There's spatial data dealing with geographic coordinates and locations for things like mapping and location analytics, and graph data structures, which represent connections like social networks or relationships. Each has its own specialized methodologies, definitely. But for this deep dive into foundational statistics, we really keep our focus on the rectangular format. That's where we start.
Okay, got it. So once we've got our data neatly structured rectangularly, that's when the real understanding begins. We're often trying to figure out what's typical in our data, right,
Yeah.
Devon, and how spread out everything is around that typical value. Let's start with what our source calls estimates of location, essentially, measuring the central tendency.
Absolutely. The most common one everyone knows is the mean, the simple average. But here's a pro tip. Don't just default to the mean without thinking. If your data has extreme values, what we call outliers, the median becomes your superhero. Seriously. The median is just the middle value when your data is sorted. And it's incredibly robust because, as the source says, it's not influenced by outliers. Imagine calculating average income in a neighborhood. If Bill Gates moves in, that drastically skews the mean, right? But the median, it would remain a far more representative, typical value. Outliers aren't always errors, mind you, but they always warrant investigation.
Right, so the median helps us keep things real when those extreme values pop up. Is there like a compromise between the mean and the median? Something in between?
There is. The trimmed mean offers a really nice balance. It basically makes our estimate robust by simply removing a small percentage, say 10%, from both the top and the bottom of the sorted data before calculating the average. For instance, if you look at state population data or murder rates, the mean, the trimmed mean, and the median can tell very different stories. Larger states often act as outliers, and they pull the simple mean significantly higher than the median or the trimmed mean. This highlights a crucial insight. Choosing the right estimate isn't about finding the most complex one. It's about understanding your data's inherent distribution and, guarding against misleading averages.
Okay, that makes sense. So beyond where the data is centered, we need to know how much spread there is. How variable is it? This brings us to estimates of variability, which measure whether data values are tightly clustered or spread out.
That's right. The standard deviation and its square, the variance, are the most widely used. But another key insight, just like with the mean, is that they are especially sensitive to outliers. Why? Because they're based on square deviations. Those extreme values get magnified quite a bit. For more robust estimates of variability, you should consider the median absolute deviation from the median, MED. This measure is much more forgiving of extreme values. It gives a truer sense of spread when you have outliers lurking. In our state population example again, the standard deviation can be almost twice as large as the MED, and that's precisely because of its sensitivity to those really large state populations. So the lesson here is, when outliers are present, your choice of variability measure is just as critical as your choice of central tendency.
That's a really critical takeaway. Yeah, it's not just about the calculation, it's about what that calculation is truly telling you about your data. Now, moving beyond single numbers, let's talk about the sheer power of actually seeing your data. Our source points out that visualizations can unlock insights that simple statistics often miss entirely.
Absolutely. Visualizations are your intuitive pathway into the data. They really are. For exploring data distribution, percentiles and box plots are incredibly useful tools. They quickly show you how the data is distributed overall. For example, knowing the median state murder rate is 4 is one thing, but knowing the 5th percentile is 1.6 and the 95th is 6.51. That gives you a much richer picture of the variability, doesn't it? Box plots, often called box and whiskers plots, visualize these percentiles and the overall spread beautifully. They can even highlight potential outliers for you.
So box plots give us that quick snapshot of the spread. What about a more detailed look at frequencies? Like how often do values fall into certain ranges?
For that, we typically use frequency tables and histograms. You group your data into intervals or bins, and histograms are simply plots of those frequencies. Imagine a histogram of state populations. You immediately see the shape of the distribution, how many states fall into different population ranges, and where the gaps might be. And for a smoother, sort of continuous estimate of that distribution, density plots are excellent. These visualizations are just invaluable because they don't just present numbers. They reveal stories and hidden structures in your data. They help you gain intuition before you even think about diving into complex models.
That makes a lot of sense. So we've looked at distributions of single numeric variables. What about when we have categorical data? Or when we want to see how two or more variables interact with each other?
Right, good question. When dealing with categorical data, the mode becomes important. That's simply the most commonly occurring category. Think of finding the most frequent cause of airline delays in an airport. That's the mode. We often use bar charts to visualize these frequencies or proportions for categories. It's a common pitfall, actually, to confuse them with histograms. Remember, bar charts show separate, distinct categories, while histograms show continuous numeric bins, usually with touching bars. Now, when we start linking categories to numeric values, we can calculate an expected value. It's basically an average based on the probability of each outcome, like that cloud technology webinar example in the source. If 5% sign up for $300, 15% for $50, and 80% for $0, your expected value per attendee works out to $22.50. This brings us to a foundational concept, probability. Intuitively, it's just the proportion of time that event would occur if you could repeat the situation countless times.
Okay, that's a clear distinction. And probability underpins a lot of what we're doing, it seems. This raises an important question, though. Once we understand individual variables, how do they relate to each other? How do we measure their interconnectedness?
That's where correlation steps in. A correlation coefficient measures the strength and direction of association between two numeric variables. It ranges from -1 for a perfect negative relationship, high x with low y, to +1 for a perfect positive one, high x with high y. 0 means no linear correlation. A quick tip, though. Always visualize correlation. Don't just rely on the number. A scatter plot is the standard way to do this. You might plot daily returns for, say, AT&T and Verizon, and you'd probably see a positive relationship as they tend to move together. But be aware of the dark cloud problem with huge data sets. Sometimes there are just too many points, and it obscures the actual patterns.
Ah, the dark cloud problem. Right. So scatter plots are great, but what are the workarounds for those massive data sets where you can't see anything?
Good question. For very large data sets, tools like hexagonal binning and contours come to the rescue. They're really useful. Hexagonal binning groups records into hexagonal areas, and the color intensity shows the count of records within that bin. It reveals density patterns really well. Contour lines, much like a topographical map you might see for terrain, highlight areas of higher data density. We saw this with the King County housing data example, plotting tax-assessed value versus square footage. These techniques can reveal subtle bands and clusters you'd completely miss in a dense scatter plot.
Those sound like powerful ways to see patterns that are otherwise just hidden in the noise. Okay, what about relationships involving categorical variables?
For two categorical variables, contingency tables are your go-to. They show counts or proportions, like comparing loan grade against loan status in a table format. And if you're looking at a categorical variable versus a numeric one, box plots are excellent again for comparing distributions. Imagine seeing flight delay percentages plotted side by side for different airlines. Finally, when dealing with multiple variables, faceting is incredibly powerful. You break down your data by an additional variable, creating multiple subplots like small multiples. For example, showing those King County housing values but faceted by zip code can reveal really interesting localized trends that a single overall plot would completely flatten out and hide.
What stands out to me here is that these visualizations aren't just pretty pictures, not at all. They are critical tools for building intuition. They don't just present numbers, they reveal stories, hidden structures in your data. They help you gain that gut feeling before you dive into the complex models. They are your first, and maybe the most important, step in understanding your data deeply.
Exactly. Now let's shift gears a bit to a truly critical concept: reliability. Because our data is rarely a perfect mirror of the world, right? So understanding sampling and distributions is absolutely key to quantifying potential errors and ultimately making robust conclusions. Even today, with big data everywhere, random sampling remains a really important arrow in the data scientist's quiver. It's fundamental. It's all about ensuring your sample truly represents the larger population you're interested in drawing conclusions about. The critical insight here is that bias, that systematic error where your sample misrepresents the population, can completely undermine your analysis. Completely. Our source makes a crucial point here. Data quality is often more important than data quantity. Remember that.
Data quality over quantity, that sounds like a lesson learned the hard way sometimes. Do you have like a classic example of that?
Oh, the quintessential example, the one everyone should know, is the Literary Digest poll of 1936. This was a leading magazine back then. They polled over 10 million people, an absolutely enormous data set for its time, and confidently predicted Alf Landon would trounce Roosevelt in the U.S. presidential election. Yet George Gallup, using a much, much smaller sample, maybe just 2,000 carefully selected individuals, correctly predicted a Roosevelt landslide. What went wrong for the Digest? They focused purely on quantity, paying little attention, as the source says, to the method of selection. They polled their own subscribers and people who owned cars and telephones back in the 30s. Essentially, they sampled a wealthier demographic which wasn't representative of the whole electorate. This sample bias meant their massive data set was fundamentally flawed, leading to a spectacularly wrong conclusion. It's a powerful, enduring lesson. Even huge data can lead you seriously astray if the sample isn't right.
Wow, that's incredible. 10 million versus 2,000 and the smaller sample one. So how else can bias creep into our analysis? Are there other forms?
Yeah. Another critical concept is selection bias. This refers to selectively choosing data consciously or unconsciously in a way that leads to a conclusion that is misleading or ephemeral. It's subtle sometimes. This includes the data snooping or vast search effect, where you just hunt and hunt through data until something interesting pops up. Humans are pattern-finding machines, right? We're wired for it, even in random noise. If you see 6 heads in a row flipping a coin, we're prone to think, wow, that's significant, when it might just be chance. The pro tip here is specify your hypothesis first, then design an experiment or analysis to test it. Don't just go fishing. Also, be aware of regression to the mean. This is where extreme values tend naturally to be followed by less extreme ones. It's a statistical phenomenon, not always a real underlying effect changing.
So we have to be really careful about how we collect and interpret our data.
Got it. What about when we actually do want to draw conclusions from our samples? How do we think about the reliability of, say, the average we calculated? This leads us to the concept of the sampling distribution of a statistic. It's really crucial to distinguish between the data distribution, which is the distribution of individual data points, and the sampling distribution, which is the distribution of a sample statistic, like the mean, if we were to take many samples. The remarkable central limit theorem comes into play here. It tells us something amazing. The means drawn from multiple samples will tend to resemble the familiar bell-shaped normal curve, even if the original source population isn't normally distributed, as long as the sample size is reasonably large. This is incredibly powerful because it allows us to use all those normal approximation formulas for statistical inference. A key metric that comes out of this thinking is the standard error. It specifically measures the variability of a sample metric, like the mean. It's a critical insight, and you absolutely shouldn't confuse it with standard deviation. Standard deviation measures variability in the data points. Standard error measures variability in the sample statistic itself. Very different things.
Okay, that central limit theorem sounds like a statistical superpower, letting us use the normal curve even when the data isn't normal. But how do we put that idea of understanding variability into practice, maybe without relying on strict theoretical assumptions all the time?
That's where the bootstrap comes in. It's a truly universal and incredibly practical tool in modern statistics. Its core idea is simple, yet really elegant. You repeatedly sample with replacement from an observed data set, unquote. By doing this many times, you create a distribution of your statistic, like the mean or median, that shows you how much it would likely vary if you could draw more samples from the original population. It's often described as an attractive one-size-fits-all method to figure out the possible error or uncertainty in your sample estimates. But a key insight is what it isn't. It doesn't magically create new data. It doesn't fix problems from a tiny sample size. It can't fill holes. It merely informs us about how lots of additional samples would behave, assuming our original sample is representative. It's about quantifying the uncertainty in the estimate we got from our one sample.
Right. And when we present those estimates, say the median income from our sample, how do we convey that uncertainty we just estimated using the bootstrap?
We typically use confidence intervals. This is the standard, accepted way to present estimates not as a single point, but as an interval range. For example, a 90% confidence interval essentially encloses the central 90% of the bootstrap sampling distribution of a sample statistic. It gives a range where we're reasonably confident the true population value lies. The factors influencing it are intuitive. More data generally means less variable estimates, which leads to narrower, more precise intervals, which is good. And a lower confidence level, say choosing 80% confidence instead of 95%, will also result in a narrower interval, simply because you're aiming to capture a smaller central chunk of the possible outcomes.
So you see, it's really not enough to just look at the numbers, calculate a mean or something. You absolutely have to understand how those numbers came to be, where the data came from, and what the inherent variability or uncertainty might be. Ignoring sampling, ignoring bias, well, it can lead you down a path of false conclusions, just like the literary digest, even with big data.
Exactly. And remember, beyond the normal distribution, which the central limit theorem points towards, data can take on various other important shapes. We encounter things like long-tailed distributions, often seen with rare events like large insurance claims or stock market crashes. There's students' t-distribution, crucial when working with small samples, or the Poisson distribution for modeling counts of events over time, like website visits per hour. Each distribution provides unique insights into the underlying phenomena, enriching our statistical toolkit and guiding our choice of appropriate methods.
We've covered a lot of ground. We've journeyed from simply looking at raw data and, shaping it to understanding its central tendencies, its spread, and finally tackling the crucial concept of reliability through proper sampling and robust estimation techniques like the bootstrap. This deep dive has really laid out the foundational statistical concepts that are just indispensable for any data scientist. Seriously fundamental stuff. By mastering these core ideas, from Tiki's whole ED philosophy of looking first to the practical power of the bootstrap for understanding overcoming uncertainty, you're not just crunching numbers. You're building a robust framework for informed decision-making, for extracting meaningful insight, and importantly, for avoiding the pitfalls of misleading patterns.
Yeah, if we connect this to the bigger picture, the true art of data science, I think, lies not just in applying the latest fancy algorithms, but in the critical thought processes these statistical fundamentals enable. It's about knowing when your intuition from a cool visualization needs to be tempered by the rigor of statistical inference. Can you really trust that pattern? It's that continuous interplay between exploring what you see in the data and understanding what you can reliably statistically conclude from it.
And that raises an important question for you, the listener, to mull over. In a world awash with data, where speed often seems to trump careful consideration, how might these foundational statistical principles, like the hard lessons from the Literary Digest poll, or just the simple power of looking at a box plot, guide you to truly surprising and robust insights, rather than just settling for the superficial observations everyone else sees?